Before continuing to learn about machine learning algorithms, we introduced the important concept of smoothing. Smoothing is a very powerful technique used across all data analysis. Other names given to this technique are curve fitting and low-pass filtering. Smoothing is designed to detect trends in the presence of noisy data, in cases in which the shape of the trend is unknown. The name smoothing comes from the fact that to accomplish this feat, we assume that the trend is smooth, as a smooth surface. In contrast, the noise or deviation from the trend is unpredictably wobbly. Part of what we explain here are the assumptions that permit us to extract the trend from the noise. To understand why we cover this topic, remember that the concepts behind smoothing techniques are extremely useful in machine learning because conditional expectations or probabilities can be thought of as trends of unknown shapes that we need to estimate in the presence of uncertainty. To explain these concepts, we will focus first on a problem with just one predictor. Specifically, we try to estimate the time trend in the 2008 US popular vote poll margin, the difference between Obama and McCain. For the purposes of this example, do not think of it as a forecasting problem. Instead, we're simply interested in learning the shape of the trend after the election is over and all polling data has been gathered. We assume that for any given day X, there is a true preference among the electorate. We will represent this with f of x. But due to the uncertainty introduced by polling, each data point comes with an error, which we'll represent with an epsilon. A mathematical model for the observed poll margin is therefore the following. To think of this as a machine learning problem, consider that we want to predict y given day x. It would be helpful to know the conditional expectation. We'll call it f of x. But since we don't know this conditional expectation, we have to estimate it. Let's start using regression, since it's the only method we have learned up to now. Here's the result. The line we see does not appear to describe the trend very well. For example, on September 4, day -62, the Republican convention was held, and the data suggests that it gave John McCain a boost in the polls. However, the regression line does not capture this potential trend. To see the lack of fit more clearly, we note that points above the fitted line, the blue ones, and those below the red line are not evenly distributed across the days. We therefore need an alternative, a more flexible approach. The general idea of smoothing is to group data points into strata in which the value of f of x can be assumed to be constant. We can make this assumption because we think f of x changes slowly, and as a result, f of x is almost constant in small windows of time. An example of this idea for the poll 2008 data is to assume that public opinion remained approximately the same within a week's time. With this assumption in place, we have several data points with the same expected value. If we fix a day to be the center of our week, let's call it x0, then for any other day x such that x minus x0 is within a week, so less than 3.5, we assume f of x is constant, so we'll say f of x is mu. This assumption implies that the expected value of y given x is approximately mu if x is within 3.5 days of x0. In smoothing, we call the size of the interval satisfying xi minus x0 being within 3.5 the window size, the bandwidth, or the span. These are used interchangeably. Later, we will see that we try to optimize this parameter. This assumption implies that a good estimate for f of x is the average of the y values within the window. If we define a0 as a set of indices I such that xi minus x0 is within 3.5, and we define n0 as the number of indices in a0, then our estimate can be written like this. The idea behind bin smoothing is to make this calculation with each value of x as the center. In the poll example, for each day, we would compute the average of the values within a week with that day in the center. Here are two examples. This is for x0 equals to negative 125 and x0 equal to negative 55. The blue segment represents the resulting average. By computing this mean for every point, we form an estimate of the underlying curve f of x. Now we're going to show you the procedure happening as we move the point from negative 155 all the way up to 0. At each value of x0, we keep the estimate f hat of x0 and then move on to the next point. The final code and resulting estimate looks like this. Note that the final result from the bin smoother is quite wiggly. One reason for this is that each time the window moves, 2 points change. We can attenuate this somewhat by taking weighted averages that give the center port more weight than faraway points, with the 2 points at the edges receiving very little weight. You can think of the bin smoother approach as a weighted average. You can write it like this. In this case, each point receives a weight of either 0 or 1 over n0, with n0 the number of points in the week. In the code we showed earlier, we use the argument kernel equals box in our call to the function ksmooth. This is because the weight function looks like a box. The ksmooth function provides a smoother option which uses the normal density to assign weights. So they would look either like this or like this. The final code using the normal kernel would look like this, and the final plot, the final estimate, like this. Notice that the final estimate now looks smoother. There are several functions in R that implement bin smoothers. Ksmooth, the one we used, is one of these. In practice, however, we typically prefer methods that use slightly more complex models than fitting a constant. The final result we just saw, for example, is still somewhat wiggly. In parts, we don't expect it to be wiggly. For example, between negative 125 and negative 75. Methods such as LOESS, which we'll explain next, improve on this. To see how smoothing relates to machine learning with a concrete example, consider our 2 versus 7 example. If we define our outcome to be y equals 1 for digits that are 7 and y equals 0 for digits that are 2, then we are interested in estimating the following conditional probability. Here, x1 and x2 are the two predictors we defined in a previous video. They represent the average amount of black pixels in 2 quadrants. In this example, the zeros and ones we observe are noisy because for some regions, the probabilities p of x1, x2 are not that close to either 0 or 1. So we need to estimate p of x1, x2. Previously, we used linear regression. Smoothing is an alternative to accomplishing this. We saw that linear regression was not flexible enough to capture the nonlinear nature of p of x1, x2. Thus, smoothing approaches may provide an improvement. In an upcoming video, we describe a popular machine learning algorithm, k-nearest neighbors, which is based on smoothing.